we're going to continue up our discussion on kinetics. Last video we had an intro. You should probably see that if you haven't already. Towards the end of our last video, we saw how the instantaneous rate in this case was proportional to BR2 to the power of 1. Now we're going to see how do we determine if it's to a different power. So this is a very common FRQ for the AP. I'll give you a table like this with concentrations of A, B, C, and the initial rate for each one. So in our last one, we were able to say that the rate is equal to KBR2. What if there's more reactants? If there's more reactants, all we're going to do is also multiply by the other reactants, maybe like Cl2, maybe by like, I don't know, J. And then each one will have to find its exponent. So how do we find the exponent of each one? You can start off by writing rate equals K times all of your reactants to some power. Now we're going to pick experiments where we want to isolate a change for each one. So I'm going to pick experiments 1 and 3 because the concentration of B stays the same and the concentration of C stays the same. However, the concentration of A changes. So now I'm able to see how the rate changes only due to A. So when A doubles, the rate doubles. That means A is to the power of 1. It's proportional to just A. Okay, if you want to write the math behind it, you could say A got doubled, so that's 2 to what power we don't know, and the rate got doubled. So that means X is 1. So when comparing experiments 1 and 3, A increased by a factor of 2, rate increased by a factor of 2, 2 to the power of 1 equals 2. That means the order is 1. We're going to do the same things for B and C now. For B, I want to pick an experiment where B changes, but C and A stay constant. So I'm going to pick experiments 1 and 2 because A is constant, C is constant, but B changes. Notice how when B doubles, the rate now quadruples. So if we write 2 to the power of X now quadruples, it becomes clear that X is 2, it's to the power of 2. So when comparing experiments 1 and 2, B increased by a factor of 2, the rate increased by a factor of 4. That means that Y, or the order with respect to B, equals 2, because 2 to the power of 2 is 4. We're going to do the last thing for C. We want something where A and B are constant and then C changes. Let's pick, for example, 3 and 4. A is constant, B is constant, but C doubles. Notice now when C doubles, the rate doesn't change. If any concentration changes and the rate stays the same, that means the power is 0. In other words, the rate does not depend on that concentration. So comparing experiments 3 and 4, C increased by a factor of 2, but the rate stayed the same. That means the order is 0. If you want to again write the math, 2 to the X equals 1, that means X equals 0. Okay? So filling out the statement at the bottom can say that the reaction is first order in reactant A, so we figured out up here. It's second order in reactant B, it's right here, and 0th order in reactant C. So to find the overall order for the reaction, we add up the orders of all the reactants. So we have rate equals K, A to the 1, B to the 2, C to the 0. So adding up these powers, 1 plus 2 plus 0 equals 3. That means the reaction is third order overall. So our final rate equation will be rate equals K times A to the power of 1, which is just A, B to the power of 2, and then since C is to the power of 0, we don't need to write C. So that's rate. We can go one step further and find the value of K. K is called the rate constant. So it's constant throughout the rate. So I can pick any experiment and it'll calculate the same K because it's a constant, it doesn't change. So I'm just going to pick experiment 1. The concentration of A is 0.1, B is 0.1, and the rate is 0.2. So I'll just plug that in. Rate is 0.2 equals K times the reactant of A is 0.1, B is also 0.1, and it's squared. And when I do that, I just isolate for K, and I solve that when you put this in your calculator, K is about 200. Now, what is the units for K? When the reaction is overall 0th order, it's molarity per second. When the reaction is first order overall, it's 1 over second. When it's second order overall, it's 1 over molarity second. So if you're catching the trend, we're dividing by molarity each time. So that means for third order, it would be 1 over molarity squared times S, and so on. Fourth order would be 1 over molarity cubed S, and so on and so forth. So here we have overall is third order, so that means the units for that is 1 over molarity squared second. So there is one other case that we have to consider, and I'll show you because it's a common AP problem where we're not able to isolate and find everything constant except 1. So let's say instead in our last problem, we solved that the order with respect to A is first order, and now we're trying to solve for B, but there's no experiment where B changes and the others are constant. So what I'm going to do is I'm going to pick 2 experiments, and I'm going to write each of the rate expressions and divide. So we know that rate equals K times A times B to the C each to their own exponent. So I'm going to write that out. Usually I like the bigger rate to be on top. And I'll show you what that means in a sec. So rate, which is 1.6 for experiment 2, equals A is 0.2. And we know that it's to the power of 1. We solve that. Times B, which is 0.2. And we don't know this power. That's what we're solving. That's going to be to the power of x. And then C, which is 0.1. And let's say we don't know that either. We don't need to know that. It'll be y. And we're going to take this, and there's k. And we're going to take this expression and divide it by our other expression from experiment 1, which is going to be rate, which is 0.2, equals k times, now the concentration of A is 0.1. We know it's to the power of 1. Times our B, which is now 0.1 to the power of x again. And then C is 0.1 to the power of y. So a few things happen. The k's cancel, and the 0.1s to the y cancel, and we're left with this expression. 1.6 divided by 0.2 is 8. So 8 equals 0.2 to the power of 1 over 0.1 to the power of 1 is 2. So equals 2 times, this is 0.2 to the x over 0.1 to the x is the same as 2 to the x, because you can write it as 0.2 over 0.1 all to the x, and then 0.2 over 0.1 is 2. So now we have a much more basic expression. So this we can easily solve. We'll divide 2 on both sides. 4 equals 2 to the power of x, and we get our same answer that x is 2. So that's how to solve if the experiments are not all constant with 1 changing. Notice how with 1 and 2, A changed and B changed, and we were still able to find it. So once you know the order of 1, you're able to find the order of another, even if both are changing, by dividing the rate expressions like this. Okay? The other method is you could say that, okay, well, A doubled, and we know that A doubles the rate when it doubles, and then B also doubled, but we don't know the expression for B, so it's to the x, and then equals the rate got multiplied by like 8. So that's the shortcut if you're able to see it. But if not, it's always good to do this to show your work. You'll get a lot of partial credit on the AP. So yeah, that's rates continued. Our integrated rate laws will be the next video. Thank you for watching.